Okay, so I'm actually really excited to see this many people here. I figured after 3 days at sea, everyone would be like, what conference? I have a fairly, if I don't blow through it, because I'm kind of nervous, but I should have enough stuff to fill up the whole thing, so cold questions to the end if you could, please. I'm a software architect at OmniTI. We do full web consulting, full stack, everything with DBA group, operations. We do a lot of performance consulting. Doing the performance consulting, we actually see a lot of battered patterns that people do, like some crazy stuff that they do in their web architectures, like having cron jobs that are run not out of cron, but out of every page load. Really, really crazy stuff. So we're here to talk about common table expressions. At my house, common table expressions tend to be things like, why aren't you wearing pants at dinner? Or, please don't stop throwing your food on the floor. But we're here to talk about common table expressions in the context of SQL. The official definition for those are temporary table definitions that exist for the duration of the query. We'll get more into that in a second. There's pretty wide support for them. Pretty much any database that you want has them, other than MySQL. So MariaDB has them. MySQL will be getting them in 8.01, but as far as I'm able to tell, there's no actual generally available version of 8 out yet. There is a development version though, so you can start using these if you really want. For all of my stuff, I will be using Postgres and Perl for all of my examples. Most of the stuff should apply to pretty much any language because it's SQL. We're focusing primarily on SQL. So the rest of it is, other than some difference in syntax or some nuances of the languages and stuff, it should be universally applicable for pretty much any relational database. So just jumping right into it, here's an example of some common table expressions. So Christmas is coming up. I know it's only July, but kids, you know. And there's a lot of effort towards renewables. So coal's getting harder to source. So Santa has a report that he needed on which regions he had shortages in. And using common table expressions, you can very clearly mark these different, you have several different sections. So we're using 2 common table expressions here, which are in the different boxes. Is anybody colorblind to red and green? Okay, good. This is the only slide where it matters. So this top box here, we're defining a common table expression. So that starts off with this with clause here. If you're following any with clause, you can have a sequence of common table expressions. And these are defined as you name the common table expression, and then as, and then inside of the parens here, you have a full query that you can do for just any type of query. And what that's going to do is replace the contents of naughty regions here with all of the report of the region and account of the children that are naughty. So later on in your query, anywhere past this point, you can refer to this just like you would in a normal table. Okay? In here we have 2 different common table expressions, and we have 2 different tables that we're going to go ahead and use at the end of our query. And this is actually like pretty cool already to me. The fact that we are able to separate our separate our common table expressions allows us to make very clear reports. And there's advantages of that, because if you have, who's had to debug someone's SQL in the past? Who enjoyed that experience? Okay. Being able to go through and make your queries these self-documenting types here makes it much easier to understand what's going on. Now, like any type of coding, it does require you to be smart, like be friendly to the person in the future. Use names that are good, like this naughty regions here, it's pretty clear what I'm trying to do, or the coal inventory. So that when we get down to our final query, what we're actually trying to do is very clear. We're just joining the naughty regions with the coal inventory. Now, everything in common table expressions, like SQL is just algebra, right? There's nothing here that I'm doing here that's all that you couldn't do without common table expressions. This is that same report without them. However, it is significantly harder to read already, even though this does the exact same thing. And we tried to use clear names as well. Like typically in a SQL, people use very small aliases for names. And we did the same thing with the common table expressions. We aliased that to n in our final join, so you don't have this gigantic name in your query. But it still allows you to be able to be more expressive in terms of how you're writing your queries for the future. Now, I think this is already pretty cool. This is one reason that a lot of our reports immediately got switched over to common table expressions. We used a lot of stuff here. You're probably not that excited about this so far. So we'll go into some other advantages, because the real advantage that CTEs come together when you put them together with some of the other tools. One of those is writable CTEs. So it's the exact same idea, except for inside of your common table expression, you can do things that modify the database, such as inserts, updates, or deletes. There'd be a very simple copy of that, version of that, which would be, here we're actually deleting from 2 different tables in one query. So that may not seem that exciting until you realize normally you have to do 2 different queries to do that. So there's also, then you start coming into the issue of like, well, do I need this to be atomic? Do I need this, et cetera, et cetera. So just kind of keep this idea in mind that you can do other things inside of CTEs, and we'll come back to that. The next key item, and this one, I believe they have something like this in pretty much every database, but here I'm using the Postgres specific syntax. This is the returning clause. So a very common thing people used to do is you would query the database to pull the next ID from your sequence, and then you insert that into your user record. So you have the ID, and then you can use that ID for other inserts you need to do as well. Later on, databases started having things like auto-increment columns. People started just inserting stuff, but you still needed to get that data back. Just a hint, like selecting that back is not always a great idea, because select max, things could have changed by then. So in here, you want to do that as an atomic operation. So we're going to insert into users, and we're going to return the user ID in the same query. So we did an insert, but we're going to get back data as if we did a select. In this case, it's just the user ID. And you can do this with more than just one column. Here, I'm going to update that same table, set the user's name to Mike, and then return everything, because somebody else might have changed something in the meantime. So I can return the entire set of the row that I modified. And if I modified multiple rows, I would get multiple rows back. So here I'm getting the entire contents of the table. So we're going to kind of take those two, and we're going to put them together with the common table expression that we saw earlier. We didn't see earlier, but the same idea. So here we have an example of using a writable CTE and then doing something else from the data. And this top part here, we're going to go ahead and delete from our children table, where these children are getting older. We're going to populate the teenagers CTE with the contents of all of the rows that we just deleted. And then we're going to insert those into our adults table. And this is all atomic. So normally, to do this atomically, you would have to start a transaction and then do multiple queries, and then commit or roll back if everything failed. Here we're doing a single query to do this. The entire thing works or fails together. In a real-world pattern, this is actually really good for archiving data. We use this a lot for, like, if you have a token that's only usable once. Well, we got it, we know that they used it, so we're going to go pull it out and put it in a different table. Transactions, being able to pull things, insert things into a ledger. If you have to, like, what's the accounting term? Two something ledger. Double accounting ledger, yeah. You can insert into both of them at the same time with the same query, etc. This is actually already a great tool for common table expressions. This next item, this is actually very Postgres specific. This does not apply to other databases. The query planner in Postgres will not optimize across common table expressions. This is awesome because in Postgres we don't have query hints. The core group of Postgres, their kind of goal is if somebody needs hints for something, we want to know what that problem is so we can just make the query planner smarter. Unfortunately, that sometimes takes a lot of political encouragement or submitting your own patch in order to get that done. So sometimes you really do need to kind of force the query planner to do something. So this is awesome that you can use these common table expressions to force your query to do certain things first, because you know that that's what needs to be done. This is also horrible because it stops the planner from doing query optimization. So what you assume is going to be the case now, and it may change over time, and then this is going to force that to continue to do the old plan when a new one may be faster. Most other databases don't have this. Their query planners will allow predicate pushdown and such into the common table expressions in order to optimize those out. SQL Server does a really great job with this, for example, or Oracle. One other item though with Postgres, if you are doing selects and you have say you have a CTE that's actually completely useless, like you don't refer to it anywhere else in the query, Postgres is smart enough to realize, oh, this isn't run, and it just won't run the entire CTE, it'll skip it because it knows it doesn't need it later. And now we're going to get into some of the really cool things that are just base SQL in terms of common table expressions that you can do. So this is recursive CTEs. So this allows you to do something that's really not possible with standard SQL, which is to have a query that refers to its own output and sort of loops. This is the literally textbook example. And you'll notice this is actually iterative, not recursive. That the SQL standard called it recursive. Everyone has to call it recursive because that's the standard. But it's actually iterative. What this query here does is it just counts from 1 to 100, which is not a really useful example. So I wanted to get something that's maybe a little easier for everybody to understand. So I want an example such as Pokemon. Does anybody know who this is?
Yes.
All right. Actually, it's Satoshi.
No.
Clearly, you watch Dubs. So Satoshi is the main character of Pokemon. For anyone who doesn't know, I help with a website called AnyDB, which is a kind of like IMDb but for Japanese animation, and they have a lot of reports and a lot of graphs and everything. Like they try to have relationships between every anime, what other animes are related to, all the characters. They tag the characters. We have a lot of very OCD people that work on this and want everything to be like absolutely correct. And so for this example, Satoshi is related to Kasumi. These guys are friends in the anime. Ash also has Pikachu and Caterpie as some of his Pokemon partners. Beyond that, Kasumi actually has her own Pokemon as well, named Gyarados. Gyarados, if he is evolved from a Magikarp, so there's a relationship there too. If everyone doesn't know, like Pokemon, you go out and catch these little things, and then like you turn them into the better stuff, and then you make them fight. It's actually pretty cruel if you think about it. And Kasumi is also friends with this character down here named Kenji. Kenji, of course, has his own Pokemon as well called Pang, and this is his specific one, but this is actually a type of Venonat. And of course, there's many other characters, and so you have like your own personal versions of them. Then there's the wild versions of Pokemon. There's different colors of Pokemon. There's all sorts of different items in here that they're all really okay. Great. So what I've described here is called a graph. These are different relations. This is actually an idea from discrete mathematics. So you have multiple nodes, which in this case are the characters, also called vertices or points, depending on who you learn from. And then you have the edges, and these edges can be one way. So a one-way relation, like I may love my wife, and I hope it's a two-way where she also loves me, but it may not be. Talk about that later, sweetheart. And these are actually very commonly represented in databases. So in the examples we have here, we have a characters table, which is very simple. Just IDs and the characters' names. And then we have relations table. And in this case, we're going to assume all of our stuff is two-way, but for the example, it really doesn't matter whether it's one-way or two-way, because it's going to work either way. So we have a from column, and we have a from column, and we have a to column, from, to, which is just the IDs of the different characters. This is standard third normal form. We're reducing things down to the minimum needed to represent them. And we're going to use common table expressions in order to do a report. Now, this is actually a very simplified SQL schema from AnyDB, but this is a report that I needed for AnyDB. Because we have a lot of issues. It's like Wikipedia, where anybody can kind of like go and add information. And we had a problem where people would add a new character, but they wouldn't add any of the relationships. And so they're like kind of like orphaned off on their own, and so they wouldn't show up on all of our graphs or anything like that when you click on the anime to look at all the different characters that are properly represented. And so we kind of thought about how we want to try to catch them all and get a list of every character. And what we wanted to do here is we figure Ash is the main character, right? So everyone knows Ash. So I can find everyone that knows Ash, and then kind of like take everyone from the anime, and then take the where that set does not intersect. So I can take the exception. Sorry, my set theory words are coming out right now. But that first part is how are we going to do that? We want to find all of the different characters that are related. And with this query, recursive query, we have the top part, which is our actual recursive query. The only difference between a normal CTE is this recursive clause, which you only have to use once, and then any sort of query after that can also be recursive. And then we have two parts to them, which I'll get to in a second. You'll also notice we have this little ID here. This is optional with CTEs. Effectively, this is kind of like your table definition. I'm naming the column here. I'm saying it's going to return one column named ID. If I didn't name that, it would follow the same rules that it would typically use for a select. So I didn't actually check this, but I think in this case it would call it 2, because that's the first named column here. Sort of if you create a table without actually like create table foo as select star from another table, it just pulls them from there. Same idea. So this has two different parts. There's the non-recursive clause, which right here is just select one, and the one here is that's the ID that we had earlier for Satoshi. This is sort of like priming the pump, sort of, you could say. This doesn't have to be just like a simple query like this. It could be a full query where you're pulling out a full set of data. But I want to pre-populate my set with Satoshi, because he's the guy that we know everybody should be related to somehow. And then we have the second, we're going to do a union. You can do a union or a union all or some other item. But typically these are done with unions. And I'm going to, in the red part here, select everybody who's related to Satoshi. And here I'm actually making a self-reference. I'm actually calling myself here. And so what this is actually going to do is it's going to run against everybody that's in the set that we pulled so far. And then we're going to iterate over that. That sounds kind of confusing, so I want to go through and show it all. So we're going to start off running our CTE. We're going to run the non-recursive clause, which is this set here. Okay. We're going to run our iterative clause, which is going to pull everybody who's related one out from Satoshi, because we're going to query the relations table. Give me everybody who's related to Satoshi, which is these three. We're then going to union that with our original set as we had in the query, which represents these guys. Okay. This will then replace the contents of the caught them all table, and we're going to then iterate again. So we took that whole set, we're going to run it again against relations, and we're going to pull one. This will then join against it and pull another level out of our relationship table. We're going to union that again. We're going to iterate again. We're going to pull the next level out. We're going to union again. And then at this point, we're not going to stop, because the query doesn't know it's done. We're going to iterate one more time, and the final iteration is not going to find anybody. This is actually the query, this is sort of like the condition for a common table expression to stop. When the last iteration and the next iteration have the same results, we didn't get anything new, that's how the common table expression knows to stop. At which point we will exit the common table expression and then finish our main query, where we're just going to pull all the names out. And that's actually a recursive CTE. This allows you to do things that just simply aren't possible in normal SQL. So effectively you can write loops with this. It's for going through graphs, which is just flat out impossible otherwise. A lot of times people would just sort of like left join and left join and left join and left join and left join against the same table, which gives you really bad performance. This allows you to do things that effectively most people are actually, like, who's heard of Neo4j? Excellent. People will install Neo4j simply because they need to do stuff like this. But Postgres and pretty much any relational database, unless you have a really complicated, like graph database, have their own set of problems that they solve. But just for doing a simple graph, there's really no reason that you couldn't do like an ancestry site or anything else just with a normal relational database. Another advantage is simplifying transactions. This is sort of like going from putting theory into more practice. We kind of mentioned this earlier, that you can kind of do more than one thing with common table expressions. With a transaction, you're doing like banking or something where you need to do multiple items as a single logical atomic operation. You need to do all of these things at once. And transactions are actually really important for things like data integrity, but they can also be really hard. And there's a few examples of what I mean by that. So this is a Perl example. This is a standard begin, commit, and then sandwich. And what the developer's done here is they've actually made a mistake. So we've gone through and we've set our auto commit, we've turned that off. We're going to do some stuff, and we're going to commit. And if there's an error, we're actually just going to go ahead and fail that out. We don't really care if it failed, we're just going to return. But what happened here is that the developer messed that up. We never turned our auto commit handle back on, which means that all of the rest of the transactions that would happen are now inside of a commit. I've seen errors like this where you get really weird stuff where nothing would end up in the database until somebody hit a certain page, and all of a sudden everything would go in. Because their stuff was broken like that. And that's really dangerous. You can understand, I don't need to go into explanations of why. You can lose a whole lot of data and not realize, just simply because somebody forgot to properly do the handle or reset auto commit. Here's an example of a pretty standard web flow or an API endpoint. We're going to go through and insert into users. We're going to return our user ID. And then since we signed up a user, we're going to go ahead and let our co-reg partner know, oh, hey, we got this. We're going to pay you for it. And then we're going to go ahead and insert the address into the address table for that user. And this is actually a really bad idea, because we're basically putting things inside of our critical path. There's a couple things that can go bad here. For one, we could have an error, in which case we're going to roll back the transaction. We're never going to know about that user, but our partner thinks we did, because we already let him know. We told him, because this isn't going to get rolled back if we have an error in the address table. So our partner thinks, oh, hey, you owe me money, and we're like, what are you talking about? We don't have that user. So clearly a bad situation. There's also huge performance impacts to this, because API calls are expensive. These are usually over HTTP, especially if you're hitting a third-party one. I've had some that where the third-party, their calls just take 30 seconds. I don't know why. If their website's down, hopefully you get an error rate back. But if there's a DNS problem or something, you could actually have a full HTTP timeout, which is oftentimes like 2 minutes. And meanwhile, this whole time you have locks out in the database. This particular example wasn't too bad of one, but I've seen situations where entire databases have gotten brought down. The entire website's locked up because a third party's API was slow. And that held open a lock. The lock held open other locks, and eventually all of their Apache children were just waiting on this one guy to finish, because they all needed to access the same piece of data, but they couldn't because this one guy was holding on to it for a third-party API call. So you want to make sure all that stuff is out of your critical sections. But it's an example of a very common error that developers make. We also have oftentimes errors, handling errors. I see this a lot when I'm looking at stuff. Here we have pretty much the same idea. We moved out the API call where it's no longer in our critical path, except it is. Here we're going to roll back if there's an error, and otherwise we're going to commit. And I see this we have this just inside as well, because we want to make sure that they both happen. I see developers doing this mistake a lot, because they forget that rollback and commit can fail. Like, just because you've gotten everything else done doesn't mean that it's actually going to go. Like, if the database dies there or whatever. So this is actually the exact same issue, but it's not a beginner error anymore now. It's like a mid-level programmer error. So how can CTE help us with this? We've kind of gone over a lot of ways to fail. How do we make it better? So here's, again, an example of a pretty common web flow. And this one actually doesn't have any errors in it. It comes down to basically 3 different sections. So we're going to insert into the users table. Then we're going to insert into the, we're going to use that data again, just like we did before. We're going to pull back our user ID. We're going to insert into addresses using that. We're going to get back our address ID, and then we're going to insert both the user ID and the address ID into our history table. This is pretty common Webflow. There's nothing really exciting about this here. But we know that we have all of these possibilities that could happen. So how do we make this simpler? And with common table expressions, you could do the same thing with this. And you're probably looking at this and like, wait, I thought you said this is easier. It's the same patterns that we've been looking at so far. We're going to create a user ID data. We're going to run our insert query and return user ID into the CTE. Now, the second CTE now can actually query against the first CTE. So we're going to insert into addresses, and then we're going to pull the user ID from user data in order to put it into the user ID for address. And then we're going to return our address ID. Same idea is going to go through for the next portion. We're doing those same inserts. We're going to return the address ID. And then our history data is going to query against both the user data and the address data to get those two IDs. And it's going to do its thing and return history ID. And then for the final query, we're just going to join those three together. Because I'm only doing single inserts, I don't even need a join condition because there's only one row in each. It's going to put all three together. I get all three IDs and return those return all three of those to the query. So that's going to take this, effectively turn it into this. We no longer need to do transaction handling because everything is atomic. We have one query. So there's much less of a chance of a developer screwing something up or putting the API call in the wrong place because there's really nowhere to put the API call wrong here. You just either after the execute or anywhere after that fetch, like it's pretty much the only place for it to go, right? If it fails, it's not going to get called because everything happens at once. It's all atomic. So I found that this is actually a really great way of, especially if you have developers that aren't necessarily writing their own queries, like someone else provides it for them because they don't know, or if you know enough from SQL to be able to do a thing like this, you can completely avoid the failure paths. Now you might be thinking, maybe this doesn't apply to me, I'm just a senior developer, I don't make mistakes. I'm just give me like a real reason to actually start using this stuff. And that's the sort of performance impact that we're going to have by doing this as well. A lot of times, I've seen devs that'll sit there and argue for hours over like what is the best way to write this loop. Like in JavaScript, should I do a for loop or should I do I minus minus? And that actually used to make a big difference in JavaScript. But those are actually, like, they'll spend all that time arguing, and we're actually only talking about maybe microseconds in terms of difference in performance per loop and things like that. And then those same devs will just be like, oh, whatever, I'll just make multiple database queries, because those are free, right? They're behind the ORM, or they're behind the function call. And those are actually really expensive, because typically a query, the full round trip and everything else, oftentimes we're talking like 10 milliseconds sometimes. Those add up very quickly. Oftentimes you'll see problems like N+1 problems and such like that, but those really grow out fast. But in this case, we're just going to kind of focus on the critical section with this item that we're working on. O of 1 scales much nicer than O of n. So, of course, we want to test those theories here. So I set up a free instance on AWS, used an RDS Postgres, and I wanted to test this with three different types of transactions. So I did 3 inserts outside of a transaction, which is kind of like very common way that people do these things. Or I also did those same 3 inserts inside of a transaction. And then I took all 3 of those inserts, put them into one common table expression, and then ran all 3 of those iterations for 100,000 times. Did each one 100,000 times. I didn't do all 3 in a row. Whatever. And it's sort of like went out of what you'd expect. Effectively, common table expressions were about roughly a 60% improvement, which makes sense, right? You're doing 1 query instead of 3 queries. And the one kind of like item of interesting note to me, inside of transactions, it was actually faster than doing them outside of transactions. Like you would actually think it would, like to me that was counterintuitive. I thought it would be more expensive to have the transaction state. But if you think about this, it actually makes sense because if you're inside of a transaction, the database doesn't actually have to write to disk. I haven't committed anything, so I don't have to write those transactions to wall. So what it would do is, inside of a transaction, is just sort of taking them into memory, and then when you commit, it writes all 3 to disk at the same time. And it gets a little bit of a improvement there. But most of our cost is actually going across the network. And so we really, most of your gain here is by using a CTE in order to avoid all of that network traffic. So this actually continues to scale out. The x-axis here is number of queries. So we started off with 2 queries and then scaled all the way up to 10. And then this is the milliseconds is over here on the side. And so you can get 60 or all the way up to, I don't know, here we're doing like 2 milliseconds, here's 30 milliseconds, so almost an order of magnitude, well, almost, of speed up on this particular little critical section here. And this is pretty amazing because we didn't change our database. We didn't change our language, we didn't add caching layer. All we did is change how we write SQL. So the only difference is more powerfully using the technologies that we already have in our stack. So there are some gotchas and some details that we want to go over. CTEs are concurrently executed. By default, Postgres does this, so they could finish pretty much in any sort of order. If order matters, make sure you enforce your ordering there. This can matter a lot, especially if you use like functions in your stuff. If I call a function, Postgres doesn't necessarily know what's going to do with that. That could cause locks, and if another one runs, then they might lock or cause like foreign key problems and things like that. But in general, that's not really an issue because we've already enforced our ordering here. We did this earlier. By making a reference to the later one, Postgres knows it needs to run the first query first and make sure everything I need for the later queries run. So that will enforce the ordering. Typically for selects, it really doesn't matter because you're just selecting stuff everywhere, so it doesn't matter how it runs. Another sort of important detail, you'll notice all of my examples, I've been using inserts. And there's a reason for that. Updates and deletes, when you're modifying the database, those cause locks. And if you're doing more than one update or delete in a CTE, you can cause problems. So here's an example of that. So we have 2 different, we're going to update 2 rows in the same table at the same time for 2 different users, right? But we have 2 threads doing this because we have an iPhone app that like does face identification or something. We're going to see like, oh, I see everybody in the crowd. We're going to set them all to the cruising because we know that they're on the boat. And we see me and Leon. But our phones see us at the same time, but in a different order. So we're going to send those to the database. So we have 2 threads coming in. But these are concurrently executing in different threads. Mine's going to try to lock the Brian row, and it wins. Leon's is going to try to lock the Leon row first, and it wins. And we're both going to try to lock the other row to do an update to it. But we can't because the other person has that row. Who knows what this situation is called?
Deadlock. Deadlock.
Yes. It's also a German, vegan, melodic death metal band, which is awesome. I had no idea until I was doing some research for this and this came on. So deadlock is like basically somebody's going to lose there. In this particular example, it wouldn't have mattered because the end result would be the same. But it's an important thing to remember because your app may actually matter. Oftentimes deadlocks are really bad. So like this particular example, we could have just ordered them the same. There's lots of different ways to handle this sort of problem. It's sort of out of the scope of the talk, but I wanted to make sure everyone's aware of that. If you're using inserts, it won't be a problem. But if you are using updates or deletes, this could actually be a problem. There's also transaction visibility. CTEs run at the same time, so they actually can't see each other's changes because they're all looking at the same state of the database. Here's sort of an example of that. I have a simple CTE speakers. I'm the only person in it, unfortunately. But I got sick, so we're going to update that and set Leon to cover my talk for me. Thanks again. But we're using this cool CTE stuff, so we're going to select the contents of that table back, try to combine that into the table. But you're actually not going to get what you think you are. Even though we updated it to Leon, this query cannot see that change yet because it's operating at the same visibility as the CTE. If I wanted to show these updates, I would need to put a returning clause here and then query against my CTE. Otherwise, I'm not going to see that. Now, if I requery it immediately afterwards, of course I will. Everything will have committed, and the next query is going to see that. But it's an important item to remember, like if you can't change rows multiple times and things like that, because they don't see each other's changes until after the thing happens. It's all one big transaction. Also, another kind of final warning, ORMs have very poor, if any, support for this sort of thing. Typically, I find that ORMs make easy things really easy, and hard things oftentimes makes them harder to do. But usually ORMs are very good about giving you a way to step out for when you really need to for performance or other complicated items you do. This would be the same here with CTEs. If you need to do that, you're probably going to have to step outside your ORM. I kind of blew through all my stuff, so I do have a little bit of extra time, so I'll go through. Here's two other cool kind of tricks that you can do with CTEs. This would be return. So we talked about earlier how you can only return data from the row that you just updated. This was an item that we needed to do for one of our partners that does Circonus monitoring. They wanted to pull some data from one table, use that to insert into another table, but they wanted to return all the data from what they just inserted, along with some of the data from the other table. And CTEs can do that. So here we're going to actually, with our source table, we're going to pull some data from an API auth token example. And then we're going to then insert that into the applications, because here they had an auth token. You had to say, okay, this auth token is good for this particular application. So we're going to insert that here. We're going to pull the data from source that we're needing to insert, and we're going to pass some in, because this is the data from the app. And then we're going to return both of those out, and then with our final query, we can pull the data from source that we care about, along with the data that we just inserted, so that we have a combined item, where we have both the data that we were going to return, as well as data that was outside the scope of that. This is actually really useful if you have things like triggers, for example, that will change the data on an insert, or some functions running in the background, where you may not know, what's going to return. For example, auto increment IDs is the obvious example with that. Additionally, here's another item that is a cool thing you can do with CTs. I'm going to, so we have a batch job where we have to take a bunch of hits and we throw them into a table, and that table gets rolled up every 5 minutes. So it's a very large table, so the analytics guys need to be able to have these roll-up tables in order to have their queries run quickly. And we live in an asynchronous world, so oftentimes we would have problems where a hit would come in very late, outside that 5-minute window. And so we needed a way to be able to clean that up easily, in which case here, we're going to go ahead and we can insert into the raw table with all those values, and then we're going to pull them out. And I'm using Postgres' upsert capability here. I don't know whether the summary table has a row for that particular item yet, so I'm going to insert it so we have a count. And if that particular item already existed, I'm going to instead update it and just add it. And I can do all of this atomically, so I'm both adding to my raw logs and to my rollup table at the same time. Again, atomically, so that there's no issues with data looking weird or being out of sync or whatever. One little quick word of warning though, this is not thread safe, because I'm doing an update here. If you have two updates coming in at the same time, they have the same visibility. And so just simply, they're both going to add to the previous value, so one of them's going to lose. So just an item to keep in mind here. This is not an issue for us because the cleanup job is single-threaded. And it's not fighting with, there's no other threads that could be happening here, so this is safe for us. But it's another cool thing that you can do with CTEs. And once you start using CTEs, I've found that oftentimes they tend to be the answer to questions I didn't know had a solution before. Like all the examples I've shown here, these were all things I needed to make really fast, and I didn't want to have to make multiple round trips. And I'm able to CTEs allows you to do multiple pulls of data And using recursive queries allows you to do loops. Both of the things are things you just can't do traditionally in SQL without using these new common table expressions. So I really blew through that, so I'm only 40 minutes, sorry guys. But overall, I'm really happy with CTEs. I think they're a great tool that people can use, especially for developers, for your toolboxes. Any questions?
You said MySQL soon. Do you know how soon?
So the developer version of MySQL is out already. So you can download, I think they have 8.03 available. I was not able to locate a general available. You'd have to ask the MySQL guys when that's going to be. But you can immediately start using it. I know this gentleman over here is using MySQL 8. It looks good so far. Depends how much you want to trust it. But they will have it soon. They're sort of like the last, like MariaDB, I think Percona has it as well. So if you're using MySQL variants, they already have this stuff. And pretty much every other database out there. Like, I think even what's the really stupid simple one that goes with it? SQLite. Even SQLite has common table expressions. So, yeah. If anybody has any questions for Ron, I'll be here for the rest of the cruise.